We're in Chapter 15. The subject is digital electronics. Modern computers are composed mostly of digital circuits. It is critical to understand the building blocks of digital circuits that comprise computer and computer-related equipment. I have another course I teach which introduces information technology fundamentals, and one of the ways that you can view a computer is that of being a binary processing machine. Digital circuits are composed of devices and circuits that are conventional in nature and repeat many of the structures we have looked at in this class, and things like transistors, capacitors, resistors, inductors. All of these things are used as building blocks for digital circuits. There are fundamental concepts and terms related to digital technology that are essential to master in order to understand their operation. The binary numbering system forms the basis for all digital logic systems and is critical to the understanding of digital concepts. And so we're going to get very familiar with binary numbering. Okay, to understand the binary numbering system, a comparison between binary and decimal is useful. So here we have a table of characteristics, and we're going to be looking at the decimal system and then comparing it with the binary. So indication of number system, and so here we have the subscript 10, and we see this number 259 and the 10 right here, and this is simply indicating that this is a base 10 numbering system. Now when we say base 10, what that means is that there are 10 digits, and so in this next column here it mentions 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice there's no 10 here, but there is a 0, and this represents 10 digits. And so the system that we're most familiar with is the decimal system, and the reason we call it decimal is because there are 10 digits. Then we have the binary system, and the subscript 2 is used, and so instead of 2, 3, 4, so on, there are just 2 digits, and the 2 digits are going to be 0 and 1, and the little 2 here tells me that this is a binary system. And just as a, if I had a number, say I had a number 1, 0, 1, 10, well, that would be representing the number 101, whereas if I had 101, that would be a binary value. Okay, so the weights of the digit positions, and we're going to go over this on the next screen here, but just briefly, you notice here that we have a base 10 systems, and we raise them to the different powers and we get different values, and so 10 to the 0. Something to remember is that any number raised to the 0 power is going to be 1, 10 to the first power is 10, 10 squared is 100, 10 to the third is 1,000, and so on. With binary, it's a little bit different experience, and we say, well, 2 to the 0 power is going to be 1, like any number raised to the 0 power is 1, 2 to the first power 2, 2 squared 4, 2, etc. And the determination of the value, and to determine the value would multiply each digit by the value of the position weight, and that would be the same in both of these. Let's look at a number and see what we're talking about when we do this. Here we have 2 values, and we want to determine what is the value of each of these numbers. Now here we have 127, and the 10 here tells me this is the base 10 number, and so we know that that equals 127. But how do we come up with that? Well, we can view this, in fact usually the typical way you did this in grade school is you view this as the ones column, this was the tens column, and this was the hundreds column. But with base 10, let's look at it as powers of 10. So this first digit would be the 10 to the 0 column. This would be the 10 to the first power. This would be 10 squared, and if we went on, it would be 10 to the third. We're not going to go there. But if we, and the last item in that previous list had said multiply each digit by the value of the position weight, and that's in order to determine the value. And so if we go to this value, for example 7, our weighted value here is 10 to the 0, which is 1. So we could say 7 times 1, and we'd say that equals 7. Then the 2 here, 2 times 10 to the first power, which is 10, would be 20. And 1 times 10 to the second power would be 100. So we have evaluated the weight of each digit, and now if we add them up, we say, well, this is 127, and we come to that value. And I mean, this is you know, students say, well, I'm not in the first grade or the third grade or whatever you do. Anyway, but this is how we would look at a decimal number. Now, with binary, a little more, it's not intuitive to us to do this. And so in this case, we're looking at powers of 2. So here we would have 2 to the 0, which is 1, and 2 to the first power, which is 2, 2 to the second, which is 4, 2 to the third, which is 8, 2 to the fourth, 16, 2 to the fifth, 32, 2 to the sixth, 64, and 2 to the seventh is 128. And so what you might notice here, here the values are going to double each time, 1, 2, 4, 8, 16, 32, and so on and so forth. Now, if these are the values that are assigned to each digit. Now, if we, this is an example here. Let's say we had the binary value of 1, 0, 0, 0. And we would look at this and we'd say, well, there's nothing for this, nothing here, nothing here. But we have a value here, 1 times 2 to the third, and we'd say that would equal 8. And if we had a value, let's add another digit. Let's say we had 1, 0, 0, 1, 1. So we would say we have a 1, which is going in the first digit, so that would be 1. And then we have a 1 in the second digit, which represents 2, so that would be 2. And then we have we have a 1 in the 16, which would be 16. So we'd have 16 plus 2 plus 1, what's that? 16, 8, what's that? 19? Is that right? 16 plus 2 is 18 plus 1, 9. Okay. And so with this larger value here we have 1, 0, 0, 0, 1, 1, 1, 1. Now, if we were going to evaluate this number, what does this equal in binary? We'd say, well, we have a 1 here, and we have a 1 here, so 1 times 2 is 2, and a 1 times 4 is 4, and a 1 times 8 is 8. And then we would have nothing here, because this is 0 times 2 to the fourth is 0, and all these numbers times 0 would be 0. Then we have 1 here, which would be 128. And if we added these up, let's see, what are we going to get? 16, 20, 22, 23, 3 carried the 2, and then we'd have 4, and we'd have 143. And so this value in binary equates to 143 in, let me get a little 10 there, in decimal. Now, if we wanted to go the other way, one of the ways you can do this, if we build I'll build a little table here and see if I can make this work. If we had, we'll make this 8 bits, 1, 2, 4, 8, 16, 32, 64, 128, and we're going to come back to this later in this chapter. But if I had this value 143 and I wanted to convert that to decimal, this is one of the easiest ways I know of doing this. And let's put out one more here, just 256, just you'll see why in a moment. So if I had this value 143 and I want to convert it to a binary value, okay, first thing, I'm looking at my table of numbers here, and would I have this value 256 to represent 143? Well, obviously, if I have a 1 right here, then it's going to be more than that value, so I would not have it. But the next question is, would I have 128? And the answer is yes. So I'd put a 1 here, and then I would take 143, and I have represented 128, so let's subtract 128. So let's see, we'll go with 3 here, and we'll make this a 10. So 8 from 13 is what, 5, and 2 from 3 is 1, and we had 15 left over. So we would not have a 64 or a 32 or a 16, but we would have an 8. So we'll put an 8 here, and then we'll take 15 minus 8, and that gives us 7. So we would have a 4, so we'll take the 4, we'll subtract 3, and so we see a 2 and a 1, so this would give us the 3. And so 1 0 0 0 1 1 1 1, that would give us our value. Now, one thing that we can do is when we're getting started in binary, it's often a good idea to check yourself with a calculator. So let's pull up our little calculator. We can do binary with this, by the way. So let's click on the little binary button here, and you notice now we only have a 1 and a 0. So let's click in that value, say 1 0 0 0 1 1 1 1. And then if we click on the decimal button, it will convert that, and we see that it is in fact 143. So I encourage you, when you are beginning to play with binary values, to check yourself out with the calculator just to ensure that you're doing it correctly. Windows also has an excellent, if you go to the scientific mode in Windows with the calculator built into Windows, you can do this with great ease. Okay, binary numbers. Binary numbers allow only 2 digits, and that should be obvious by now. We only have zeros and ones. A binary digit is called a bit, and if we have 8 of them in a row, we call that a byte. An 8-bit digit would be, okay, this is an example of an 8-bit digit. This would technically be called a byte. Microprocessors work with a variety of bit widths, including 4, 8, 16, 32, 64, 128, and more. We probably won't be dealing with much more than 8 in this class. It gets very cumbersome when you start dealing with 16 and 32, 42 bits, especially when you're trying to calculate what is that in binary. The radix point separates the integer from the fractional portion of the number. So in this case, this would be 2 to this would be the 1 point right here, and then if we added more bits, that would represent a decimal that, for example, we had 128.2 or something. And we're going to be dealing with whole values, so we won't be dealing with it, but if we say the radix, we're talking about this point right here. Okay, numerical sequences. Counting in binary is very simple and follows the same rules as decimal numbers. In decimal, we count by incrementing the least significant digit to the next highest digit value. It works the same way with binary numbers, except the highest digit value is 1. The table to the right counts to 10 using 4 bits of binary. So with the way you would do this, and this would be with 4 bits, we would start out with, you start out with 0, and then we would go 1, 2, 3, and this looks a bit different. This would be 4, 5, 6, and then 1, 1, 1 would be 7. And then if we add 1 to this, then we go 1, 0, 0, so that would be 8, 9, 10, 11, 12, 13, 14, and 15. And so we would say 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we could say 10 here. We're going to be looking at another system called hex, and if we were looking at hex, we could call this 10, but we're going to say A, and then B, C, D, E, and F, and the F here would be, no, excuse me, not 1, 1, it should be 1, 1, 1, 1 right here, excuse me. So the F would be the value for 15. And 15, by the way, is the largest number that you can represent with 4 bits, and that would be represented, if it was hex, it would be by F. And if we wanted to go to 16, note we need another bit, so that would go out here to 1, 0, 0, 0, 0. Okay, so we've introduced this wonderful system we call binary. We counted in binary. We looked at the concept of a bit and a byte. Then we did some converting of binary to decimal and decimal back to the binary, and we will be playing with that quite a bit in the chapters or the sections that follow. And we did some comparison of the characteristics of binary and decimal. And this concludes the first part of section 15.